All right. So we're going to talk about sequential data. In particular, hidden Markov models. Um, so this is the front part of chapter 13, and we will devote 2 sessions to it. As you know that like you encounter sequential data a lot, right? Search suggestions, typing suggestions, and many, many more. Before we start, I just wanted to, there are 2 updates related to assignment 2. For those of you who are still working on it, there's an updated package script fixed by the student. It's basically recursively zipping the files where the original script wasn't. And then the autograder timeout is bumped up. So if you are vectorizing your code properly, it shouldn't take more than 10 or 20 minutes. But if you haven't, it's probably not worth vectorizing now if you're in a crunch to finish it. So today we're going to cover basically the front part of hidden Markov models. And next time we're going to look at inference of hidden Markov models. The meta take-home message for sequential data is that so far we have encountered data that are all IID. It's good to have exposure to at least one example of richer data structure so that once you encounter like sequences or graphs or trees, you would have done it once, right? And this is also essentially an application of graphical model nomenclatures that we have been living and breathing in the last little while, and then essentially using the same machinery on sequence data. We will revisit the sum product algorithm under yet different names, and then we would also look at the EM algorithm again. So here's another example of sequence data. I would say this is what, if you have a smart speaker or if you talk to your phone, this is what they hear, right? There are at least 4 kinds of sequence representations that are often used. The middle one is the amplitude, right? So for a piece of speech or a piece of music, it's essentially the same representation except the structure of the sound is slightly different. For a piece of speech, we can have the waveform, which is basically how much, if it's a speaker, how much the membrane of that speaker like displaces the displacement over time of a vibrating device, right? Whether it's your vocal cord or the speaker. And as you can see, this part is a voice region. And then if we look at the frequency domain, frequency intuitively represent like high pitch or low pitch. Like men are usually, vocal cords have lower pitch than women. And these horizontal streaks represent what's called formants, or basically the voice parts, mostly vowels, in our speech pattern, right? So what's being said is Bayes' theorem, right? As we can say, right, this vowel part Bayes is, we can see clear frequency structures. Basically, there are like what's called the first fundamental frequency and higher frequencies. And then the vowels, especially the unvoiced vowels, they're essentially friction in our vocal cord, and they show up like this. The third kind of sequence information are what's called phonemes. Basically, they are individual sounds. For English, you can essentially read it out. In Bayes' theorem, the B sound is a phoneme itself, and then the vowel following is another sound itself. And the last kind of sequence information are sequence of words. So you can see that like your phone or your smart speaker will need to basically go from the waveform. So going from the waveform to the Fourier domain is pretty standard, although in the age of deep neural network, this part has also been revamped or reinvented, or you can actually learn a frequency representation nowadays. Before that, the most prominent like representation is called mel frequency that's supposed to line up with our ear band. And then from this represent the symbol or phoneme sequences, and then from phoneme sequences recover the word sequences. So Ella is asking a question, why is Z higher frequency than I? Yeah, right. Excuse me. Yeah, this is a good question. As I said, the voice sounds are, if you put your hand in your vocal cord, you can like basically just on your throat, you can feel your vocal cord vibrating in nouns and what's called voiced consonants, right? And then for most of the consonants, it's sort of just what is the right word? It's been a while since I did this like speech session. Basically, your vocal cord don't vibrate with principal frequencies like this. There's no horizontal streaks. They're just producing a noise, right? By sort of yeah. Either there is a transient sound explosives such as B, or there is I'm not sure the right word, right? The word come to my mind is friction right now. Okay, sibilance. Thanks, no, for helping. I will have to look it up. But basically, it's basically on the like sounds like th or z show up as a bunch of noise on the higher frequency range. It doesn't mean there is nothing on the lower frequency, just this is more prominent. And so things that essentially smear out in the frequency domain, they sound like noise rather than like vowels. Or if you were singing, then these formants or fundamental frequencies of your voice will line up with like the appropriate frequency in the instrument. I hope that's okay. Anyway, speech and sound are always a fascinating topic. I could go on about them forever, but let's look at sequence data in general. I hope that's okay. So feel free to ask me questions after this workshop. So far, we actually haven't seen this kind of data, despite they're everywhere. It's not just speech, right? We have videos. You have your phone actually knows where you are once you turned the navigation on. So these are sequences, right? So if we look, right, DNA sequences are sequences. But so far, our data that we look at in this class has been IID. Even for a sophisticated graphical model with lots of variables, the joint distribution assumes that the whole vector of x is drawn IID from the graphical model or base net. So just like in your assignment 2, there are 10 variables, but you get like 5,000 student records to learn the graphical, to perform learning and inference of that graphical model, right? We can also say that a lot of times sequential data present itself in the form of data over time, right? Speech, video, and so on. But sometimes, a lot of times it doesn't, right? So the data index is not time. such as, let's say, for DNA sequences, it's just 3 billion base pairs organized into 26 long sequences, and the index is just where the base pair sits in the long DNA sequence. And words in an article are not indexed by time, it's just which word are said before or after which other words. There's another case where temporal data is also a fascinating subject, which I personally worked on for a fair bit in the last few years. And the data index doesn't have to be uniform by some common notion, right? For example, if we have, suppose we go to a bus stop and with a stopwatch, and then we record when the interval between which people arrive at the bus stop. So we assume all persons are just persons. It is the inter-arrival time, the length of that, or the variations of that matters. Because we know there will be a first person, the second person, and so on. The index doesn't really matter. It's actually when, over time, when the event happens, matters. So a similar model can be informed. So these are so-called stochastic point process models. You can imagine, for example, failures of infrastructure in a city can also be seen as a sequence of time steps. Right, so there's, if you have studied statistics, there's a large class of what's called survival models that models these. So in terms of, so for now, for this particular section, we're not going to look at where the stochastic process version of sequential data. We're just going to assume we have a sequence, and the index means something, and it's sort of more or less uniformly interpreted. It's not necessarily time. So there's a few other terminologies, right? So when we talk about distributions of sequential data, so what is P of X now, right? So if we have, are we talking about the marginal distribution of P of X little n for n goes to 1 to n? Or are we talking about the joint distribution of P of big X, essentially X from 1 to big N? Or are we talking about a condition of Xn condition of Xn minus 1 or n plus 1? There are many possibilities. So one crucial assumption that allows us to simplify and extract statistically meaningful patterns is stationarity, right? It refers to the case that the data evolves in time, but some underlying distribution from which it is drawn remains the same. The thing is, since these are sequence data, and if they are indeed drawn over time, we can't wind back in time to draw like 1,000 different sequences. If we don't have this kind of assumption, it will be hard to model. Of course, there are different kinds of non-stationarity. So exactly how to define stationarity is also beyond the scope of this particular session. In the stochastic literature, the process literature, there's a few ways. I'm not going to go through them. If you're interested, ask me. So for now, we're just assume some distribution remains the same over time. So let's try and use the tool of graphical model for sequences. And starting from the naive and not very interesting case, right? So the most naive approach to modeling a sequence is to ignore the fact that it's a sequence. And we observe, we have observations x1 through xn. And in this case, the joint distribution is trivially written out since they are independent of each other, P of x1 times P of x2 all the way to P of xn, right? There is another extreme of modeling sequences, which is in a fully general form, as we know from Bayes network. If we have a numbering over our variables, we can just make the higher numbered variable conditioning on all of its like predecessors, basically. For every n, xn conditioned on x1 through n minus 1. So what kind of graphical model is this then? So we have, okay, also like before, I'm going to draw 4 steps. Now we have x1, x2, x3, and x4. And the dependency will be x1 is the first variable. It doesn't depend on other stuff. x2 depend on x1. And then x3 depend on x1 and x2. x4 depend on everything before. So the link here and the link here. As you can see, this gets quite busy. And this doesn't, like the full dependence, fully general sequence model essentially is treating the whole sequence as a fully connected Bayes network. And this doesn't quite help, right? So as our sequence length grows, this graph grows. And it's hard to estimate conditional probabilities tables that are like high dimension like this. So for convenience, I mean, there's HMMs are quite versatile where the distribution of X can be continuous and so on. It's easier to learn it like assuming that things are discrete. Basically, whenever you see a variable, you assume it's binary or has a handful of discrete values. And we worry about changing summation to integration a bit later. So we've also looked at Markov chains when we learned Markov chain Monte Carlo, a few weeks ago. So at that time, what we did was we said states or samples form a Markov chain where the next state depends only on its immediate previous state, but not earlier states. Right, so this corresponds to a factorization as follows. The graphical model will form a chain, and we can simply write it like this, where the conditioning is on the immediate previous variable. We could generalize the notion of Markov chains and form, let's say, high-order Markov chains, because you may say that, oh, if I'm at x4, forgetting everything before x3 seems to be a bit stringent. Can we do better, right? So indeed, we can essentially form a second-order Markov chain by making every variable from the third one onwards conditioning on its 2 immediate predecessor variables. So, and you can keep doing this and have essentially a fixed order Markov chain, which requires you to maintain a fixed size memory and not potentially infinite memory like the page before. There's also another interesting note. If we allow vector-valued variables, which we should, conceptually it makes no difference, we can actually convert higher-order Markov chains to first-order Markov chains. So you do this by essentially take a like cross product of the variables, right? So instead of writing like you make a variable, a vector, x1, x2, x2, x3, x3, x4, x4, x5. And now, once we made the state space larger, we essentially convert this higher order Markov chain to a first order Markov chain again. This is because I can say that the probability of the joint probability of x3 and x4 depend only on so for x4 given x3 and x2 can be captured by like this term in the middle and that only. All right, so that's a bit heavy, but conceptually, basically, if we make like larger states, Markov chain, fixed order Markov chains can be seen as like specialized cases of first order Markov chains. So that's an extra reason for us to care about first order Markov chains. So this is a flashback slide where in sampling we said that we have, back then we were looking at sample variables z, and probability of z condition on the history is equal to z condition on its immediate predecessor, and the marginal probability is basically the transition probability of z m plus 1 given zm, and then marginalized over zm. Right. The chain is called homogeneous when the transition probabilities remain the same over time. Basically, no matter which time slice it is, let's say, equally likely if I'm going to the classroom, given that I'm at a cafe, and vice versa. Excuse me. And the chain is called stationary or invariant if the marginal probability of z are the same. And it's called ergodic if the chain converges to an equilibrium distribution, no matter what the initial state distribution is. So these are just reminders. We will use a slightly different subset of these properties here. So we pretty much covered the second order Markov chains. We're just going to proceed, right? So in terms of representational flexibility and modeling complexity, we could easily see Markov chains generalizing to continuous variables. In the rest of chapter 13 that we won't have time to go into, so you can have linear Gaussian conditional distributions. Basically, if the x is Gaussian, and the conditional probabilities of the next x conditional the current x is also Gaussian, we get autoregressive models. We can also model the conditional probability with, let's say, a neural network, right? Pushing to the extreme, I would say some of you would have seen or used a recurrent neural network. You can think of that as an implicit high-order Markov chain, right? The current state is a function of the previous state and the input, and also the hidden state of the recurrent new unit that essentially encodes some information from all the previous states. So you may say that the Markov model is still limited, right? You say that, well, I don't want to be limited by the Markov assumption of any order. If I wanted to take cross product of the states, that's kind of a pain. If I just want a model that's first order, but is also very flexible, what else can we do, right? So in comes the hidden state. And in the book, it's introduced as the state space model, right? So this is the first picture of hidden Markov models, right? So in here, before we were just looking at x's depending on each other. And right now we're looking at, there is a hidden state sequence called Z. Remember when we look at Gaussian mixture models, we were just looking at a single slice of this, right? So there is the mixture component where X is Gaussian condition on the hidden variable Z. Now we just string essentially series of mixture components, mixture models together. So what this allows us to do is in here, the x's potentially have arbitrary dependencies to each other. Because the z's are not observed, right? For xn plus 1, it depends on xn, but it also depends on earlier x's, just because we would need to marginalize out the different value of z's. And this graphical structure applies to the hidden Markov model where the state is usually discrete, and linear dynamic systems where the state and the observation can also be continuous. So if we want to understand this using the graphical model nomenclature, here's how. Remember our discussion on directed and undirected graph and moralizing? So there is no coparent of nodes. If we moralize this graph, we just remove all the arrows, right? We can see there is always a path connecting any two observed variables, xn and xm. If we ignore all the arrows, nothing is deseparated or conditionally independent of another variable if we don't condition on anything. As you will see, despite this flexibility, the prediction for the xm plus 1, it can still be efficiently computed, because once we conditioned on some of these latent variables, let's say if we assume we know what Zn is, then xn plus 1 is actually deseparated from all the previous z's and x's as well. Right, so for this session, we're just going to say, oh, we have discrete latent variables, and then observations can be discrete or continuous. In particular, if we have speech, the observations of waveforms or spectrums can be continuous, but if we have, let's say, words, then the observations are also discrete. Let's proceed by looking at hidden Markov models a bit more. In particular, the representation for hidden Markov model is that we're using one of k encoding scheme for the latent state z of n. Assume each of these latent states have one out of k possible values. So in the next 3 slides, we're going to see 3 different drawings of hidden Markov models. And the 3 graphical representation. So there are 2 or 3, like the reasons we are taking the trouble to do so is that are twofold. Is that we think it will help us understand what's really going on. And then as a historical note, hidden Markov models are developed by the speech community in the 60s and 70s, where large telephony companies and defense funded lots of research on speech recognition. For example, you might know the timid benchmark dataset that are still used by, like, as toy dataset, which is essentially recognizing digits or phone numbers people spoke, right? Back in the day of people need to call up a switchboard and like tell a human what number they need to dial, automating that seemed to be very pertinent, right? So historically, HMMs are developed before the complete vocabularies of graphical models were available and fully fledged. So therefore, there are a number of different views. And each of these views and help us understand different parts of the algorithm differently. So here are the parameters of HMM. Now we have the ZMs. We encode the time invariant transition matrix A of JK as the probability of Z n, taking the small k state given the previous state Z of n minus 1 taking the J state, right? So this A matrix is a k by k matrix, and then it's positive, it's non-negative, and then it's in this case it has row sums to 1, the row sum to 1. This is a probability of Zn as a vector given Zn minus 1 J. And if we observe what these hidden states are, then the probability of the whole sequence of latent states is simply the product of the corresponding entries of the corresponding transition matrices. So this should be pretty straightforward, right? If this is state like state 1 and state 3 and so on. So for this transition arc, we simply take A1, 3 as the entry and multiply them together. So you say that, well, okay, these A matrices take care of all the transitions. What about the first state, right? So we need a probability for the first stage. This is called prior. It's denoted by pi. And it's encoded in the same nomenclature by raising to the power of the 1 of k, 0, 1 encoding of Z1. And only one of these entries in this big product is active, of course. Okay, so that's the graphical model representation of HMMs and probability of hidden state. Here's the second representation. You say that the hidden states are discrete. So why don't we just write them out, right? For example, we could imagine each of these correspond to different phonemes. Let's say this is the phoneme B, this is the phoneme EH, and so on, right? And the actual phoneme space is, of course, much larger than this. And then because we assume that the transition matrix is fixed over the sequence, we can see that if we connect all pairs of these states, we can essentially write the values of the transition matrices in all of these pairwise arrows, including self-loops. So why is this helpful, right? Okay, we don't get to see an example yet, but the reason that this is helpful is that it can visualize constraints, if there's any, on the basically subsequent states. Right, so in English, for example, if this is a consonant, and so the consonant to vowel transition is a lot more likely than consonant followed by another consonant. It's possible, right? Similarly here, vowel to vowel transition is also a lot less likely. And if we're looking at people moving across different locations, let's say I start at home in the morning, and I'm more likely to go to work, and then I go eat, and then maybe I go to work again, and then I return home, right? It's maybe less likely that I just have arbitrary transitions, right? If I'm spending a day at work, then not all of the transitions are active. So this particular representation is good for visualizing constraints like that. It's also good for visualizing if there are hierarchical states, right? You can imagine, let's say the eating state, it can have substates, right? Depending on which cafe you're going to, right? Cafe 1 or the way to cafe N. And then in terms of work, you can be in the office, the meeting room, the classroom, the tutorial room, and so on. So you could unroll this the states hierarchically, and that's useful too. So here's representation number 3, which is useful when we talk about inference algorithms. This is called the trellis or lattice representation. The book prefers lattice, but if you read some of the old classic literature on HMMs, it's called the trellis. What it does, so the book has this consistent notation that this sig square nodes are values in the state space. So it's sort of similar to the previous one, except it's unrolling the state space over time, right? So this previous view is useful, but time is lost. It just says we're making transitions, and also observations are lost. So now let's bring time back. To do this, we're just going to copy the same 3 states, and then we're just going to draw the same arrows between states in adjacent times, and the values of transition matrix can still live on the edges. And if you notice in the graphical model view, right, so we have z of small n influencing x of small n, right? And there's temporal arrows going on either side of z of n, meaning x of n is conditionally independent of the rest of the whole hidden Markov model given z of n. So what this allows us to do is that there's another parameter called emission probabilities. Basically, the probability of x conditioned on z, we assume there is a different distribution, basically a whole row of conditional probability tables for x, depending on which value of z it is, and we use the same notation. So you can think of these as essentially scores living on each node, right? So this lattice representation unrolls the state space, and it's making conditional probabilities more intuitive in a sense. Most of you would have dealt with this in assignment 2, right? When we simply write P of X conditioned on something, we actually mean like a whole matrix, right? Or a high dimensional matrix. So this representation is making it more explicit. So putting all of these representations and probability and some parameters together, what do we get? Here it is. Our variables are a sequence of x's observations and then a sequence of z's latent variables. The joint probability of these 2 sets of variables is basically a product of the prior times the product of the transition probabilities times the product of emission probabilities. You can verify this by seeing that the x is conditioned, it's independent of the rest of the chain conditioned on the corresponding z, and z is independent of its predecessor's condition on the previous z, and we have some probability with z1, right? And the parameter set, denoted as big theta, essentially has 3 parts. The parameters for the prior, parameters for the transition, matrix A, and the parameters for the emission, we call it phi. It can be Gaussian or a table, right? So this picture makes it more concrete for us. Assume we have an HMM that has 3 hidden states, right, colored in the same as our state space view. And the emission probabilities are Gaussian. So condition on each state value, let's say it is green state, x is a Gaussian around it. And by the way, the centers of these Gaussian are fixed, right? Same goes with the blue and red cousins. And moreover, this the transition matrix of this HMM is fixed so that in any state there's a 5% probability of making a transition to any other state and a 90% probability of remaining in the same state. So it has a tendency to stay in the same state for a while, and then with 5% probability jump to either the red state or the blue state here. So this is if we sample from this HMN, this is what we get. Assume we start from, because it's kind of symmetric, it doesn't mean like it's the probability of reverse sequence is the same in this case because of symmetry. We can assume we start from here. We draw the next state, right? We're in the green state and we draw an X, and then we draw the next state, which is, it says blue, I'll go to blue. And then it actually stays in blue after we draw subsequent states until it decides to jump to red. And maybe back to blue again, or maybe back to green and back again. Anyway, so you can kind of see the visually, it's quite rich of a sequence where it jumps across different parts of this probability space, right? So back to when we talked about sampling. Remember, one of the challenges of generating samples for multimode distributions is to be able to jump across different modes, right? In here, what this graph illustrates, it's what's called an ancestral sampling scheme, basically by decomposing a complex distribution into two parts, and if we model both which hidden state it is and what is the distribution x given z, we could actually jump across different modes, which is an aside. Right. There's another like interesting exercise you could do is that given this particular hidden Markov model, what is the expected duration that the HMM stays in state 2 once it's in state 2, right? So how long do we expect the HMM to stay in any given state? There's another interesting question you could ask yourself. It is how long will the HMM stay in state 2 given that it's already in state 2 for 10 steps? Meaning that if I'm already in the red state for 10 steps, do the distribution of me staying more there change? The spoiler is that it doesn't because of the Markov property. I'll leave you to sort of digest that. As we said, one attractive application of the state space transition diagram is to visualize the structures inside the state space. So in this particular case, from state 1, I can skip a state and go to state 3, but once I'm in state 3, it's what's called absorbing state, right? So I cannot go back to either 1 or 2 again. So this could be desirable. Say I'm done for the day, I'm not gonna get out of my house once I'm there. But it also imposes constraints, right? So the equilibrium distribution will be in state 3, right? And the corresponding lattice for this left to right HMM also has a couple less links, right? So we can see that state 1 can go to state 2 or stay put. State 2 can go to state 3 or stay put. State 3 can only go to itself. Actually, this particular diagram is missing a couple of edges. If it corresponds exactly to the above, state 1 can also go to state 3, like this. Easy to spot. Right, so for the defense of the book, it's meant to draw a 3-state left to right diagram where the state value is incremented by 1 and not like have arbitrary left to right jumps. Just wipe it out. So you may say, oh, how do we use this right left-right structure? The book contains an example of handwriting recognition. So this is an app that a lot of us use right now. For example, where I'm writing on an iPad, and you know that our phones and tablets can recognize the letters and numbers we write these days. And these are being, like applications being developed essentially in the turn of the century, the late 90s and 2000s. The encoding of the writing is pen direction. Right. It basically says it's 16 directions of the pen. Assuming that we sample the pen directions. In here, we're not looking at images, right? Because if we're working with a tablet or like stylus, we have more information about which pixel is hit first, right? So we have, let's say, it's 8, and this is 4, right? So this is like 8 directions of pens. Just imagine this. I won't try it, it gets too busy. Like if we do 16 direction encoding, it's like half as accurate, or the angles are half what's here, right? And we enforce the left to right transitions because each HMM encode a digit, right? Now we assume that there is some canonical writing that has 16 states, and then our observation has 16 states. Therefore, the emission distribution is 16 by 16. And the task is to pick the most likely or best HMM for data, right? Writing sequence. And this corresponds to a digit, right? The advantage of doing so in the left to right state transition is that these left to right state transitions allow us to have some flexibility of what's called local time warping. Or you would, if you looked at the literature, you would see the word dynamic time warp. Basically, different people speak at slightly different speed, and sometimes when I'm in an emphasis, I might pause and sort of elongate a syllable. Same goes with writing, right? So at different times, even the same person write at different speeds. So the left to right transition is allowing that by saying, oh, maybe this is staying in the same state. And of course, if we're having a left to right structure, we cannot accommodate reversal of writing sequences. It's not possible, unlike the Gaussian example before. So the top 3 pictures are sequences of training digits. And after being trained, or the model has seen a mere 45 handwritten digits of 2, we asked the model to spit out some digits, right? Basically perform sampling using this expression and the learned parameters. So here's what it does. It spits out something that looks like a 2, but still not quite there yet. So that's promising. It means that it has learned the like topological structure of 2, but somehow the size wasn't there. Some of the underlying limitations of HMMs is that, as I kind of hinted, the distribution of staying in the state is exponential. So meaning it tends to favor shorter state times depending on what the value of A1, like the self-transition loops is. Maybe this is the explanation of these tools are kind of smaller and shorter than the training tools. So here's another example, not from the book, but developed in like previously in this class. So assume we have 2 students, Peter and Mary. let's say Peter is in Canberra, Mary is in Sydney. They communicate often, but don't observe what each other does all the time. Peter is a CS student and only interested in riding his bicycle, shopping for new computers, and studying. Oh, okay, this is a stereotype of, let's say, computer science students. Here, just bear with us with the poor analogy. And we only care about what he does, like that depend on the weather because that's the hidden state. Mary does not care to track weather in Canberra every day, but she knows the general trends, right? She also knows Peter well enough to know that he does on average on the rainy days and when the skies are blue, right? So when the skies are blue, get out and ride the bike a bit more. She believes that the weather follows a given discrete Markov chain, and she tries to guess the sequence of weather patterns from knowing what Peter told her what he did. So here is the model. Assuming it's Canberra, right? The background probability of it being sunny, like today, despite it's quite cold, is 0.8. Being rainy is, let's say, 1/5. And the transition probability between a rainy day to a rainy day is 0.3, and a sunny day to a sunny day is 0.6. And it's more likely to be sunny tomorrow, even if it's raining today. And the emission probabilities are as follows. If it is a rainy day, then Peter most likely does shop and study, and only occasionally still go out for cycling. And then if it's a sunny day, he doesn't study much, right? He cycles and shops. That means maybe overall Peter tend to cycle and shop more because sunny is by default more likely. So Peter tells Mary that the list of his activities in the last 3 days was cycle, shop, and study. So he's covered the whole spectrum. So the machine learning problem you would want to solve is calculate the probability of this observation sequence given this underlying model, right? And also calculate the most probable sequence of hidden states given these observations. So we can use the trellis diagram by unrolling it like this. So because the states are discrete, we're denoting the emission probability using curly arrows. So the straight arrow part is the trellis we saw. We begin with 1/5 chance of rainy, 4/5 of sunny, and then we make transitions according to the transition matrix. And then at each stage, we write out the probability of cycle, shop, and study on the edges. You can see that these probabilities don't change over time, right? The emission probabilities are stationary as well. So if Peter says that his activities were cycle, shop, and study, you wonder, how do we compute this? The two questions on the last page. To see the intuitive complexity of it, we begin by thinking, hey, can we basically just pick the most likely state for each of these observations, right? So if Peter's shopping, does it mean that it's more likely to be rainy the second day and it's more likely to be rainy the third day and it's sunny the first day? That seems overall not too likely given that the transition from sunny to rainy and rainy to rainy is not very high. Right, so we can't just greedily pick the most likely state. In fact, there is non-zero probability, let's say, of being in either state given any activity, right? So ideally, these square nodes are hidden. We will want to some overall possible values. So if we were doing this brute force, we will need to do this. like, so I'm going to abbreviate as like rainy, sunny for the state value. So if we're going rain, 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 then we essentially need to trade off the probability of rain, 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 and the initial rain, and the probability of, let's say, cycle given rain, probability of shop given rain again, and probability of study given rain. So if we look at the, basically this is the probability of state variables, and then this is emissions. In computer science terms, we can't really prune out any state sequence before we computed both sets of terms for all possible state sequences, right? So in this case, it's 2 to the 3 different state sequences. So this is the complexity of sequential data, essentially. We can't easily rule out like states over time. We have to marginalize over them properly. Let's say this is obviously relevant for like applications such as speech, right? For example, if so things say I'm not a native speaker and I tend to get some of the consonants wrong. Let's say be a Bayes theorem, I get the th wrong and I sometimes get the z wrong too. But you can still understand me, but that's because despite the emission may be unlikely, like for example, if I pronounce th as s, but looking over the whole sequence, you can somehow correct that, and that's very important for yes, deal with real world variations. So more formally, we are going to tackle the following machine learning questions that we care about. As we said, there is the problem of inference, which we will spend a lot of time on next time. And then there's the problem of learning. The inference basically says, given the model theta, like in the last page, we know what Peter's behavior and weather transitions are like, and observation sequence X. We would like to know what is the most likely state sequence in Z, right? So let's say e.g. speech recognition. And then we would like to compute incomplete data likelihood. Basically, what is the P of X given theta, right? This is relevant if we're doing, let's say, 10 written digit, right? We want to evaluate P of X given theta for the digit 1 versus P of X given theta for the digit 2 and so on, and pick the more likely, right? And well, because we're looking at a hidden variable model, we wonder what the complete data likelihood is, right? By now you've seen EM a few times. You know that this term is kind of useful. And you will also wonder what is the probability of a partial sequence, right? So these are algorithmically useful quantities. Basically, if we can build divide and conquer and like compute the probability of the partial sequence, we can get a probability of the entire sequence. We can of course compute marginals and also let's say marginals for a particular transition as well. These are good for diagnosis. So for learning, we assume given the model structure, basically given what the state space looks like and the form of the emission and transition probabilities, like are they tables or Gaussians, number of states, and observation sequences. So usually multiple observation sequences. How do we estimate theta? Okay, we're at an hour. We're going to spend a bit of time actually talking about the learning. We're going to ignore the inference for today, assume it's done for us. This is sort of a big ask, but because you have learned graphical models and EM algorithm, we ask you to assume that can be done, and exactly how that's done we cover next time. Yeah, so today let's look at the learning. And yes, we're going to assume that we have some of these quantities. It's a luxury, but we can just assume whichever thing we want, and then try to work out how to do them next time. So here is the maximum likelihood. The complete data likelihood, right? So there are x variables and z's. If we assume everything is observed, we get this. Now we have x observed and z latent. From EM, this strip is familiar. We look at the incomplete data likelihood if we marginalize over z, right? As we saw in the uni student example, marginalize over z requires like k to the power of n terms, right? If we then do it brute force. Moreover, these ZNs depend on the previous ZN, right? So that's, yeah, doesn't help computationally. So we're still in this exponential complexity realm. So there are two general strategies. We assume that we can use the EM algorithm, and hopefully we get an efficient version of EM algorithm over the chain. And then we assume we use the E step to compute P of Z given X. And then the M step, so this is just a recap of the generic view of EM algorithm. We maximize this expected complete data likelihood, which is a function of X, in fact, and also theta. So for the first term, we plug in the current theta. The complete data likelihood is nice in that it's a product of terms. We take the log, we can essentially pull them apart. And we then maximize this Q term with respect to theta, right? The theta nu. Then we're done. So that's the EM recipe plugged in here. So now we define helper quantities that we want to learn how to compute next time. We like this P of Z, like the vector Z given X and theta is still too complex, right? It's the probability of the whole sequence. It's a joint probability. Now we assume we break, like divide and conquer, and compute these gamma terms. So they look similar to the gamma terms in Gaussian mixture models. So for each observed Z, assume we can compute the marginal posterior, the posterior of Zn given the entire sequence of X and the current theta. We also assume we can compute the joint posterior, basically the joint between two adjacent states, given X and the entire sequence and the current parameters. So as you can see, we can, right, this is related to the transitions directly. And this one is directly related to the emissions and other things. And the initial probability if n is 1, right? So because now we notice that this is a vector of 1 of k encoding, right? So we unroll this representation to each of the k components of Z. Basically, the probability, the posterior probability of Z taking the k's value is as follows, right? Which is not news. It's basically the fraction of times that this particular Z and K is expected to be active. Similarly, we do the same with this transition matrix, right? So this is a matrix. And then this is essentially like, you may see in some literature this is shorthanded as Z, well, C of JK, and then you somehow need to denote the time. So coming up with the right notation is hard. I would say the book does a really good job of making everything explicit. For example, the book notation is better than this other one because it's making which variables is being modeled explicit, and there's a typo in the book as well. It's easy to spot and fix. So now we've defined all of the posterior probabilities. Now we plug it into the Q term to see what it gives us, right? So Q term is the posterior upfront times the log completely likelihood summed over Z, right? So we first remind ourselves that log complete data likelihood is the product of three groups of terms. Assume now we have the gamma and C. So we know that P of Z, 1 through n, given x theta old, would be essentially gamma of Z1k times C of say Z2j, which one? Okay, yep. Z1k, Z2j, and so on and so forth, right? So the probability of a particular hidden state sequence is essentially the product of these posterior terms. You can verify that using Bayes' rule. So we use the log to pull apart 13.10. And we end up with this particular expression, right? So the initial probability term is multiplying pi, and the transition term is multiplying log of A, and the emission probability is multiplying the gammas for the subsequent bits. So these are nicely separated because in this summation over big Z here, if you plug in this term probability, you can see we essentially marginalize out the Z's except the gamma Z and K in this term. So we like maximization problems where we get a sum of expressions of unknowns. In this case, we can just, when we take the derivative with respect to each of them, or the other term vanishes. So treat the gamma and C's as knowns, right? So if we do that exercise, we can see that similarly to Gaussian mixture models, the pi k terms are essentially the expected fraction of the k's entry of the initial state being active. We can similarly normalize, right? So the transition probability is summing over all positions in the sequence and normalize the corresponding row. So these are intuitive. I'm not going to derive them in detail, although I trust you can do them by either citing the maximum likelihood result for the multinomials or using Lagrange multiplier, imposing the phi k and ajk sum to 1 over k. You can derive similar expressions for the phi. Like if the book has the expression written out when phi is p of xn given phi k is Gaussian distribution, it should look similar, and it's sort of it's an intuitive check about whether you're getting like sensible estimates. So that's what we wanted to say about sequential data today. We looked at different ways of drawing the hidden Markov model. We discussed different forms of sequence data and try and motivate that this is an important class of problems. Hopefully you will agree. For those of you taking, let's say, document analysis in the next semester, a document is a sequence of tokens, and you will be doing this a lot. And there are different tags for analyzing sequences in natural language, such as part of speech, tagging, like whether this is a noun or verb or adjective, entity tagging, whether we are looking at a term which is part of a name entity or not, and many others. So next time we're going to cover forward, backward, and inference for HMMs, and also an instance of max sum algorithm, which is called Viterbi algorithm. That's all. Are there any questions? Just going to stop the recording.